Okay, so now we are recording as well. Okay, couldn't start recording. Okay, let's see what's wrong. Start. Okay, now it's recording. Okay, so okay, let's begin. Okay, so group 3A and group 4A. First of all, what is the first member of group 3A? Okay, what are group 3A elements? Group 3A elements are the ones that have how many electrons in their outer shell?
3 electrons.
3 electrons in their outer shell, correct. So let me just turn on my pen. Okay, so now it's on. Group 3A and group 4A. Two very important chapters. Let's start. Okay, group 3A elements and group 4A elements. These are the normal elements. Okay, they are non-transition elements. And group 3A contain 3 outer shell electrons, 3 valence electrons, whereas group 4A contain 4 electrons in their outer shell. Okay, now group 3A, you need to know the electronic configuration and everything as well. So group 3 has aluminium as the most important element in it. Okay, aluminium has a proton number of 13. You should know that aluminium is a metal which has amphoteric nature, right? When it forms oxides, they are amphoteric in nature. And do you guys remember the meaning of amphoteric oxides?
It can act as a
Yes,
base and an acid as well.
exactly. So they can react as acid as well as bases. So aluminium, and it also the oxides of aluminium Al2O3 can act as very good catalysts as well in a lot of reactions that we might have seen already in organic chemistry, especially. Aluminium, its electronic configuration is 1s2, 2s2, 2p6, 3s2, and 3p1. Okay, now the third shell contains 3 electrons in total. Okay, there are 3 electrons in the valence shell, therefore belongs to group 3, and the block which it belongs to is the p block because the outer electron is present in the p orbital, hence it group 3A belongs to the p block, the periodic table. Okay, these are some general properties of group 3A elements. You have other elements as well in the same group. Now, its properties are going to be exactly similar to whatever properties you'll see in any typical group, meaning going down the group, you'll observe the atomic radius to increase, okay? Ionization energy will decrease, and then melting and boiling point will also change accordingly. It will melting points also vary in a meaning melting points don't have a specific trend, like it increases and decreases. Okay, boiling point density, everything is covered in a table given in the book. This is table 3.1. Table 3.1 has data on group 3. Okay, but all you need to know is the trend, the general trend of each one of these properties.
Sir, could
Okay,
you please tell the page number?
yeah, so it's basically page number is the first page, page 37, the first page of the chapter, page 37. Okay, now atomic number, you already know that it will increase. Electronic configuration, you know that it should stay in the p orbital. Ionization energy will decrease. Electron affinity will also vary in a different manner. Now electron affinity is variable, so just look at the trend. The general trend is enough. Okay, then electronegativity. Electronegativity has a clear-cut trend. Electronegativity going down the group, it decreases. Okay, down the group decreases because radius is increasing. Apart from that, the atomic radius, we just saw that it going down the group increases. The ionic radius also increases. Melting points are variable. Boiling points are also, boiling point have a trend. Boiling point decreases. Okay, boiling point decreases. Then density has a trend. Density increases down the group. Okay, because the size of the atoms increase. That's why. So density increases down the road. These are the general specific trends given. Okay, so you could just know the trends. Then next very important element of period three, group three. Sorry, group three. One is aluminium and the other one is boron. B, boron. Okay, aluminium and boron. Now, boron and aluminium. So now it's time to talk about boron. Boron, it's not a very abundant element, not abundant. Okay, and certain compounds of boron are very important for your exam. Boron is found not naturally as an in combination with oxygen. These ions are called oxyborate ions. Okay. Similarly, some minerals are given in the tables over here. Out of these minerals, borax is a very important mineral. Borax is also called tinkle. So this is a mineral, okay, mineral of boron, in which boron is found, and its chemical formula is Na2B4O7.10H2O. Now this is very important, okay. Borax is important. Then, because it has been tested, similarly, silicate is also important. Silomenite is important. It's Ca2B6O11.5H2O. Then we have orthoboric acid, which is also important. Orthoboric acid is H3BO3. Okay. You can, now these are very important. Then apart from this, we also have another table 3.3, which are common minerals of aluminium. So the in aluminium, cryolite is important. Minerals of aluminium. Cryolite is important. Apart from cryolite, we have bauxite, which is a principal ore of aluminium. The formula of cryolite is sodium aluminium fluoride NaF6. Okay, and the formula of bauxite is Al2O3 dot 2H2O. Okay, bauxite is also called alumina. Diaspore is also important. These are the ones that I've seen in the past papers. Okay, I've not seen any other apart from these. But if you want to stay on the safe side, you may remember the rest as well. But again, in the first attempt, like in the first go, just remember the ones that I'm pointing out. Okay, so that you can just get done with all the important stuff first, and then maybe prepare the rest later. Okay, this is diaspore. So these are the principal elements of aluminium. Then let's talk about some peculiarities that boron have. Peculiar behavior, as I mentioned previously as well, is very important. Okay, peculiar behavior of boron. Okay, so how is boron different from its from the rest of its elements? Basically, I told you that there was a diagonal relationship, right? So that's why boron stands out and has different properties. Okay, so boron is the first member of group 3A again because it is the first member. So it's mainly because of diagonal relationship. Okay. Okay, now it's the first member of group 3A. This is group 4A. So if this is boron, it must have properties similar to the second element of group 4A. Okay, or I should say it should have properties similar to group 4A elements. Okay, let's just list down the most important properties of boron first, and we can move on then. Okay, because it belongs to the it's the first member, so it will have properties different from the rest of its group. Okay, and first of all, it's non-metallic in nature, and that's something unusual because the rest of group 3, like majority of it, is metallic. Okay, and group 4 elements, you guys know, are non-metallic, right? Some of them are metalloids, some of them are non-metals, but none of them are
Sir,
metals.
why boron is non-metallic?
Well, that's because of the diagonal relationship I just told you, right? It's a non-metal. Diagonal relationship, it has properties similar to group 4A. Group 4A are non-metals, that's why it's going to be non-metal. Okay, and plus that's one property, the exact reason why it's non-metallic is not given in the textbook. So the only reason that's given is because of the diagonal relationship. That's it. Okay? And then it's non-metallic because it doesn't have properties similar to metals. Like it does not conduct electricity, it does not have shiny appearance, stuff like that. Okay? Make sense? Okay? Intaha?
Yes, sir.
Okay, second property that is peculiar about it is that it is the only element that has less than four electrons and still non-metallic. Okay, its valence shell has how many electrons? Valence shell have less than four electrons, right? It's the only non-metal. Sorry. Yeah. So it's the only non-metal with less than four electrons. Okay. Usually metals have less than four electrons and non-metals have more than four electrons. But this is again the only non-metal that has less than four electrons. So that's another peculiar behavior. You guys just need to remember them. Okay. The reason for why it's a non-metal specifically is not there in the syllabus. Okay, and even I don't know it, so you don't know it, need to know it. It will not be tested. Let's move on. Boron always uses all the three of its valence electrons for bonding purposes, so it has fixed oxidation states of +3 or -3. Okay, these are the fixed oxidation states, and it will always use this. These are always, this is always the case. Okay, then moving on. One of the outstanding features is the ability to form molecular addition compounds, meaning it can form molecular compounds. Molecular compounds. What do you mean by molecular compounds? Yes, meaning it can form simple covalent compounds. Remember simple covalent and giant covalent, it can form covalent bonds. All the group 3 elements, which are usually metals, will form ionic compounds, right? But boron does have covalent bonds as well. For example, boron chloride, BCl3. This is a covalent structure. Okay, If you form boron, attach boron with three chlorine atoms, it's going to be covalent. Okay, can someone tell me the bond angle and the shape of this molecule? It has no lone pair, only three bonded pairs. So what is it? The bond angle is going to be 120 degrees, and the shape is going to be trigonal
Primary.
plane. Okay, and then finally, it does not form ionic compounds. It sulfates nitrates or other anions because it does not form a stable cation. Okay, so no ionic compounds. Okay, I hope that makes sense. Let's move on. Now, next we need to study about the compounds of boron. The most important ones that are given are borax. Borax, as we mentioned previously as well, is important, right? It's Na2B4O7.10H2O, right? Sodium tetraborate as well. That's another name of this compound, sodium tetraborate. Now, as I said, boron and borax and stuff related to boron are very important. So, sodium tetraborate is the name. This has been tested. Okay, and how is it formed? So, basically, it's the sodium salt of tetraboric acid. Okay, this tetraborate comes from an acid which is called tetraboric acid. Tetraboric acid. When the tetraboric acid reacts with sodium or a compound of sodium, let's say it reacts with sodium hydroxide, it's going to form the compound. Okay, or in the textbook they have reacted it with sodium carbonate. So it doesn't really matter, when both of them react, they will result in the formation of sodium tetraborate. Okay. Okay, and another MCQ that came previously, although wasn't expecting it to come, but it did come, and that is its occurrence. This borax is found in Tibet. Okay, do you guys know where Tibet is? Does anyone know where Tibet is? Well, I didn't know that for a very long time, but then I got to know a few days ago. Where is Tibet? Any guesses? Okay, right now I'm quite close to Tibet. I'm sitting quite close to Tibet. Now, can you guess it? Borax is basically found as natural deposit called tinkle. It's found in the form of tinkle in the dried lakes of.
China.
Yes. Oh, you just search it up, didn't you?
You said that you're in Hong Kong, right?
No, I never said that. I said I'm
No, you
sitting on.
said no, you're near that place. You're
Yeah,
in
it's in.
Hong Kong. Yeah, right?
Yes, yes. It's a state of China, Tibet.
Yes.
And there's just a fun fact that planes don't fly over Tibet. You guys know why?
No.
Because it has a mountainous terrain for a very long range, so planes won't be able to land. So that's very dangerous. Okay, so it's all mountainous. People who live there, the Tibet people, they are the people who live in mountains. So it's a very good, like a very famous tourist attraction as well. Anyways, so tinkle is borax is found in the form of tinkle in the dried lakes of Tibet and California as well. California is in the USA. You guys know that, right? Already. Okay. So, how is this tetraboric acid manufactured? Three steps are given in the textbook. So, we can just go over them one by one. Okay. First of all, as the name suggests, boric acid. So, boric acid formula is H3BO3. Okay. You can call it boric acid, you can call it orthoboric acid. It's up to you. Okay. Both of them mean the same thing. When it reacts with sodium carbonate, This equation now is the most important one, okay? Rest of it we may not remember, but the equation is super important because it's chemistry, so it's all about equations. So Na2B4O7, solid. This is that salt which we are studying right now. What is this salt called? Borax, right? Or sodium tetraborate. The sodium tetraborate has been made along with, obviously, this is an acid reacting with a carbonate, right? So, what are the three things that we get when acid reacts with carbonate? We get salt, we get water, and carbon dioxide, right? So, yeah, and the balancing is also given. It's very important. So, there you go. This is your boric acid. Boric acid reacts with sodium carbonate to give you this thing, the sodium tetraborate or borax. Borate. And by the way, this boric acid can also be called tetraboric acid. Okay, same thing. Okay, एक ही चीज के दो तीन नाम है, so don't get confused. Apart from that, this is like the formal borax. Formerly, borax was manufactured by treating a hot solution of boric acid with the proper amount of soda ash. What is soda ash? This name is repeated very frequently. Soda ash and caustic soda and other sodas. Okay, remember this has to be a hot solution. This was the formal technique. Nowadays there's a different technique in which a silomic acid, silomenite is used. See, I told you silomenite was important because it has equations. This is technique number 2. Okay, in silomenite you have CaB6O11. Okay, this silomenite, which is a solid, reacts with again the same substance, soda ash, and it gives you three things as well. It gives you calcium carbonate, CaCO3, sodium tetraborate, along with another compound of sodium and boron. I don't really know the name of this. Okay, nor do you guys need to know because it's not in the syllabus, no, nor in the textbook. You just know the equation. And so if you balance it, this is a sort of formula you get. Solaminite is important. Solaminite. Okay. Then finally, okay, so this is obtained from this is called calcium borate. Okay, this is a compound of calcium and boric acid. Okay, selaminite or also known as calcium borate. Okay, now so it's finely powdered and boiled with sodium carbonate solution. So when this precipitate of calcium carbonate is uh, formed, then the clear solution which contains this mixture is tapped off from the top and allowed to crystallize. Then the crystals of borax are separated out. You get more borax, carbon dioxide is then blown through the mother liquor, and so the sodium metaborate is decomposed into borax, which separates to form this thing. Okay, so let's talk about this. Okay, the name of this compound just came. This is called sodium metaborate. Okay, then what happens? You get this. This is a clear solution. Clear solution is removed from the top. Okay, Now, this clear solution is allowed to cool and crystallize. Okay, this is the clear solution. Now, this clear solution is allowed to crystallize. So when it crystallizes, what happens? Crystals of sodium, uh, crystals of sodium tetraborate are they crystal out. Okay, allowed to crystallize, and so borax crystals appear. Borax crystals separate out. Now, once the borax crystals separate out, meaning this is also gone. Okay, this is gone because the clear solution had these two things, right? It had borax along with sodium tetraborate, sodium metaborate, NaBO2. Okay, इन दोनों का मिक्सचर था. Now when you allow it to crystallize, crystallization से क्या होगा? Next step is removal of borax. Borax crystallizes out. Crystallization. A borax निकल गया. What is left behind? This is called whatever is left behind, meaning after the borax goes out, this mixture that we are left with. This mixture is called the mixture from which the crystals have been removed. This is called mother liquor. Okay, mother liquor. Now this mother liquor has sodium metaborate in it. Okay, NaBO2. Now what we do is if we want more of the borax, we start bubbling carbon dioxide gas through it. Okay, so when carbon dioxide is bubbled through this through sodium metaborate, then this reaction occurs in which sodium metaborate combines with carbon dioxide and forms sodium carbonate Na2CO3 along with borax. Again, more borax is formed, Na2B4O7. Okay, so these are the steps involved over here in the modern method. We start off with calcium borate, react it with sodium carbonate, and we form a mixture of calcium carbonate, which is a solid, a precipitate, the borax or sodium tetraborate, and sodium metaborate. Now we take this clear solution, this is our clear solution, and crystallize it. Okay, have made a crystal around it. So this clear solution is allowed to crystallize. So when you crystallize it, borax crystals they just separate out. Borax crystals separate out. When borax crystals separate out, whatever is left behind, it contains sodium metaborate only. It's called the mother liquor. Now, if you need to you need to obtain more crystals of sodium tetraborate from this mixture. You're gonna bubble carbon dioxide through it, and then you're gonna get the product as sodium carbonate again, along with more borax. Understood? So this is the modern technique of synthesis of borax. Is that clear, guys? Anything you want to ask over here? Question two. Sir, background voice. Oh, sorry about that, Naila. Can you hear me now properly? I hope the background noise is gone now.
He's not in the class. I think my net went out.
Oh, okay. Can you guys now just tell me, did you understand question number two, the step number two, or
Yes.
you didn't? Yes, Muntaha,
Yes, sir.
understood it. Okay,
Yes.
and uh, how about you, Naila? All good about this one?
So she's not in the class when that went off, I guess.
Oh, okay. All right. So if this is clear, let's move on to step number three. Okay. Now, the third method by which it's synthesized is by treating tinkle with water. Okay. So what is tinkle? Basically, the formula of tinkle was already there in the table up there. Okay. Tinkle is basically the crystallized form of borax, sodium tetraborate or borax, same thing. Okay. This is sodium tetraborate Na2B4O7 dot 10H2O. So this is the crystallized form of borax. So tinkle is actually in the form of crystals. If we just react it with water, okay, just take tinkle, add water into it, because tinkle is a dry solution. Remember, dry. It's a dried up form. Dried crystals are there. Okay. If you add water into it, okay, this mixture that you get, the solution that you get, then you heat it. Okay. If you heat it, then you are left with borax crystals. Okay. By heating, again, they're referring to which process? The same process of crystallization, crystals formation. Okay. And as more and more crystals separate out, you keep on heating the solution. Okay. Crystals, just separate them. Okay. And you continue heating the clear solution. Okay. So with this, you'll get more and more crystals. Right. So the three methods by which borax is synthesized are completed. Okay. One, two, three. Methods of manufacturing borax.
Sir,
Yes.
tinkle itself is a form of borax, right?
Yeah, with 10 water molecules. And tinkle is also used as the naturally occurring ore of borax. Okay. In the lakes of Tibet and California. Like that's the natural ore from where you'll find it. Okay, then we next step we need to move on to studying the properties. So properties, point number one is mostly reading. Okay, meaning it's white in color, it's this and that. So if any MCQ comes from here and you might have studied it, then you'll be safe. If you've not studied it, then you won't know it. Okay, so this is more like learning stuff. But what is important here? It's sparingly soluble in cold water, but more soluble in hot water. And then at a different temperature, you'll have different shapes coming out that can be tested. If a saturated solution is allowed to cool above 62, you'll get octahedral crystals of the pentahydride. If the temperature is below, then you get decahydrate crystals. Its aqueous solution is alkaline in nature due to hydrolysis. Okay. So that's a point I think you should remember. The rest of it you can just read it off, but this is important that its aqueous solution is alkaline. Okay, and I'll tell you the reason. It's alkaline because of hydrolysis that occurs. If you have sodium tetraborate, Na2B4O7, okay, this is sodium tetraborate, and you add it to water, so it reacts with water and it forms two things. It forms sodium hydroxide, which is a very strong alkali, as you know, along with the orthoboric acid or the boric acid again. Boric acid, remember, is a weak acid. Okay, and this is a strong alkali. No, sit down. Oh. So it's because of this strong alkali, the solution is alkaline. Okay, then next is, and yeah, if you want to prevent this reaction from occurring, you can add glycerin into the mixture. Glycerin can act as an inhibitor, prevents hydrolysis. Okay, then when heated, the borax can lose the water and form different things. So let's see. The second property is on heating, just simply heat borax. It's going to give you a bunch of things. Okay, it can lose the water, Na2B4O7. 10H2O, heat it, and then you get Na2B4O7. This is your borax again, but it would not be a specific shape. It's just gonna look like a glassy mass mixture. Okay, but obviously it's gonna be this thing, along with sodium metaborate, Na2, NaBO2, along with B2O3. Okay, and this is called the borax bead test. There's a test called the borax bead test. That's also has been tested. This is the basis of the borax bead test. Okay, why is this the basis of borax bead test? So basically we take borax, we heat it, and it's gonna form glassy beads. This glassy mass is actually gonna be your bead. It will have a beaded appearance. Okay, so if that occurs, if you heat a substance and it gives you this beaded appearance, and that means yes, borax is positive, borax is present. Okay, so borax loses water when heated and it swells up into a white porous mass due to expulsion of water. Okay, this is a glassy mass, but it's white, glassy mass, white and porous as well. Okay, okay, someone texted. Someone, okay, it's from NASA. Okay, let's continue now. So we have, it's gonna form a transparent glass-like white porous mass due to expulsion of water. Okay, water has been removed. Previously, it had water, but now it doesn't. And then if you further heat it, it's gonna become clear, transparent glass. Okay, if you heat it further, if you heat this glassy mass further, it's gonna form clear, transparent glass. Once you have the clear, transparent glass formed, You can dissolve it in metallic oxides. Okay, you can dissolve in different metallic oxides. After dissolution, you get colored beads. This is the full explanation of the borax bead test. Colored beads are formed. But again, the basis of the entire all of this process is this basic reaction. That's the base of this reaction. Okay, so let's just erase the bead mark over here. And this is a white and porous. Okay. Then moving on, third property of borax is aqueous solution can react with acids, because you know that aqueous solution is alkaline, right? So if you have an aqueous solution, Na2B4O7, in the aqueous solution, that's a requirement, okay? Without it being dissolved in the aqueous solution, it will not react. When it reacts with HCl, and because it's added in aqueous solution, so it will react with water as well. When it does that, you expect to get sodium chloride, meaning the sodium salt of the acid, which reacts with it, along with boric acid, again, H3BO3, the weak acid. And then you can balance the equation. Okay, then now this is the third step, okay? And you can have a reaction with sulfuric acid as given, but the only difference would be the salt. Okay, if you have sulfuric acid added here, SuSO4, then you get sodium sulfate instead, Na2SO4. Okay. Okay. Now after this, step number 4, the fourth reaction, that's when borax is heated with ammonium chloride. Okay. You know that alkalis, when they're heated with ammonium salts, they will produce ammonia gas. Okay. So in this case, you don't get exactly ammonia, but you do get a gas similar to ammonia. Not very similar, but yeah, you do get a gas of nitrogen. It's called boron nitride. This is the sort of reaction. Na2B4O7 reacting with ammonium chloride, NH4Cl. It's going to give you sodium chloride along with boron nitride, along with B2O3 and water. I'm not balancing it out. You can see the balancing from the textbook. And then the fifth one is when it is added, dissolved in water, it can ionize as well. Okay, because it's just an ionic salt, right? If you add a solid, dissolve it into water, you can have sodium ions and just the borate tetraborate ions as well. Okay, but of course you know that we've just seen it just now that the tetraborate ions they don't remain in the dissolved state for a long time, right? They can hydrolyze, meaning they can react with water. So when B4O72 negative reacts with water, it's going to form the boric acid, H3BO3, as we've seen in the previous reactions as well, along with hydroxide ions. Because of which it's an alkaline solution, it's because of this hydroxide ions. Okay, so this is a strong alkali. So this is an pH is more than 7. Actually, it's very close to 13 or 14. Okay, then the borax bead test is given again separately as well. Okay, let's just revise it quickly. The salt. Okay, so in borax bead test, you have to prepare a loop at the end of a platinum wire. Heat the wire and take a little powder of borax on the hot loop. Heat it again. Then borax will first swell up and then melt into colorless glass-like bead on the loop. And then now put a few grains of the substance under examination on the beads and reheat it. First in the oxidizing flame, then in the reducing flame. That's the method. So the chemistry is borax when fused is decomposed into sodium metaborate and boric anhydride, and then the metallic oxide formed from the substance under examination combines with this giving the colored metallic borax. Okay, so what is borax bead test used for? It's used to test for metallic oxides. Okay, so what you do is you take a platinum wire, this is a platinum wire, and you make a loop at the end. And then what do? You heat it. Okay, you heat it over here. Once you heat it, you're gonna next add powdered borax on the hot loop. Okay, on the hot loop, you're gonna then next add some borax. This is you've already added powdered borax onto it. Then what will you do? Once you add powdered borax, this powdered borax is gonna convert into, as you know, the glassy substance first. It's gonna swell up and converts to the white glassy substance. Swells up first and then converts to, well, I think it's better if I just mention the term, it melts to. Colorless glass-like bead on the loop. Okay. Now you have a colorless glass-like bead formed over here. Once that happens, what do you do next? You take the substance under examination, which is probably a metallic oxide, right? So you take the unknown substance and then next you add on to it. Okay? Okay. Okay. So substance under examination is then added. That's the next step. Once you add that substance under examination, then you reheat first in an oxidizing flame, followed by reducing flame. If a metallic oxide is present, you will get colored bead, meaning this colorless bead is going to convert into colored bead. Okay, that's the entire procedure. Let's now study the chemistry behind this procedure. Okay, and then you first take a platinum wire, you heat it, you loop it, you heat the loop, then you add some borax. Once you add powdered borax, it's going to swell up. Then you add the substance under examination, and then you reheat in an oxidizing flame and then a reducing flame. What happens then? So the chemistry is simple. When you heat borax first, it's gonna break down. It swells up and breaks down, right? It swells up and melts into sodium metaborate along with boric anhydride. Okay, this B2O3 is called boric anhydride. Sodium metaborate, okay? Okay, so this happens when it's heated, okay? When it's fused, I mean. Then the metallic oxide formed from the substance under examination combines with B2O3, giving the colored metallic borates. Okay, so this B2O3, it's gonna react with the substance metallic oxide produced from the unknown substance and gives colored beads. Colored metallic borates. Okay, now what is the significance? Well, we already have a standard of these colors, like we have already tested them, and we know which color is given by which metal. For example, copper can give a red color or blue color. Cupric oxides, the beads are blue in oxidizing flame, but cupric borates are blue in color. Okay, so yeah, that's one example. Okay, for example, you have this one, cupric oxide. It reacts with B2O3. What was B2O3? Boric anhydride. Then you get copper, BO2, 2. This is that colored metallic borate. Okay. And what color is it? The cupric oxide. The beads are colored blue in oxidizing flame. Okay, because cupric borate is blue. This is blue. So with this, we completed the borax bead test. Okay, methodology as well as the chemistry behind it. This is entirely the method. This is entirely the chemistry. A borax bead test. Right. Once we are done with borax bead test, let's move on to some uses of borax. I think I'll just skip the uses of borax because you just need to read them. So no rocket science, no understanding needed. I'll just move on to boric acids. There are different types of boric acids, and they're all very, very important. Okay, uses, just read it. Okay, now we're going to move on to different types of boric acids. At least you should know the formula and the names of these. And I think that's all that's given, how one is converted to the other. Okay,
स्टार्ट करेंगे
right. So the first one is called, basically we call it boric acid, like the main one. We call it boric acid, but its actual name, according to this terminology, is orthoboric acid. Okay, this is the one that is also known as boric acid. Like if the term boric acid is used on the exam, they are actually referring to this one. And its formula is H3BO3. You already know that, right? A lot of students get confused here because a lot of students have studied boric acid. This has boric acid, and if the name orthoboric acid comes on the exam, they are confused. So just ensure that orthoboric acid and just boric acid are exactly the same thing. Okay. Then number two. Okay. All right. Number two is metaboric acid. Then number three is tetraboric acid. Number four is pyroboric acid. Okay. Now the reason why this one is called boric acid is because all of the other ones can decompose into to form this one. Okay. Metaboric acid. Third one is tetraboric acid. And then the fourth one, pyroboric. One second, guys. The screen, I think now is got frozen. One second. Okay. Muntaha, are you in class?
Yes, sir.
Okay, good. So the formula of metaboric acid is
Sir,
HB.
आपकी screen is not shared.
Okay, I think it just got stuck or something. Let me reshare it. Is it shared now? Hmm?
Yes.
Good. Okay. I think इतनी recording पहले मीटिंग के लिए 1 घंटे की काफ़ी है. I'll just stop the recording.